So a few quick notes before we get started. I didn't get to it today, but the link for the proposals is now online. So if you go to the assignments page, you can submit your proposal. That's due Friday, but since it was delayed, I might push it just back till Monday. It's not going to really hurt anyone to do it on Monday. So I'll send an announcement after class, but those will be due Monday instead of today. I was a few days late posting the announcement, so let's just, or the forms, let's just have it just due on Monday. The other thing is that, so I've sadly didn't quite catch up at all with notes over spring break, but so I'm posting some incomplete ones currently, and I will catch up with those this weekend though. So those by Monday, at least everything up to the current lecture will be posted before class on Monday. Or some bad consequences will happen, like everyone gets hundreds on the next homework or something like that. I'm just saying that so I have to do it. Okay, so the last thing was that there was a post on Piazza I saw was posting the poll for today that says that there was an equation that you couldn't quite see on the slides last time. Does anyone remember what that was, and if they need it done again? I can just post a direct response on Piazza, but the problem with this thing is that there's no indication of where the actual field of view is, so something that slips out of the field of view. But does anyone remember what that was that I was writing and people couldn't see? If not, I'll just write it on Piazza, but if this was an issue for everyone, I'm happy to just do it right now. Does anyone remember? It was one of these ones, maybe? One of these? Okay, that's fine. I'll just look at the video again and try to post it if people don't remember. Okay, today we're going to do two things. Today we're going to first of all go through some common probability distributions, which last time we sort of covered some basic rules of probability. We're now going to, very quickly I think, because we're not really going to talk about them in detail, but we're going to cover some number of kind of traditional distributions that you typically will see in a lot, or that at least frequently come up in a lot of data science tasks. And then we're going to switch from probability to statistics. So we're going to start talking about how do I actually estimate from data the best parameters of a distribution. And that's going to be really the remainder of the lecture. And in doing so, we'll cover actually a number of algorithms, including a number of machine learning algorithms, kind of viewed in that manner, like least squares and logistic regression. We'll also cover the naive Bayes algorithm, which is a new algorithm really based upon probabilistic modeling. So we're going to go kind of fast through this, but we'll hopefully get through all of it. So there's a few distributions that are sort of good to know about. And the simplest distribution there is, in some sense, is the, let me switch this to this, hang on. This, and I want this. Okay. So the simplest distribution there is the Bernoulli distribution. This is a distribution over binary random variables. And we write it the following way. We say that the probability of a random variable x being equal to 1, so x, little x here, will take on values. Man, I'm doing it already. Okay, there we go. Little x takes on values. It's really, there's just no indication of where it actually is. Takes on values in 0 and 1. The probability that the random variable equals 1, parameterized by phi, and I'll get to this notation in a second, is equal to phi. So what does this mean? So in general, we're going to write distributions this way. We're going to write them as the probability of some event. When we talk about probability distributions, they're specified by some number of parameters. We're going to write them as the probability of some random variable equals something, then a semicolon, and the parameters that govern that distribution. So here, this is a simple distribution. It's just Bernoulli. That means there's only, can take out two values. There's only one parameter that governs this distribution. It's this parameter phi. Phi is just a number between 0 and 1. It's just the probability that it's just defined as the probability that is equal to 1. But the important point here is that this phi is the parameter for this distribution, for the Bernoulli distribution. In other words, depending on what the value of phi is, I obviously have a different distribution, right? One that has a half of a chance of being 1, one that has 75% chance, etc. So this is very simple here. There are more complex examples we'll get to in a second. But this is sort of how we're going to write distributions here. Okay, and so from now on, and we're going to do this a lot actually, sort of from now on, we're going to write this distributions kind of in this way. And this is going to be a probability of some event, and then semicolon, listing all the parameters that govern that distribution. Right? And that's going to be our notation for how we describe distributions that are, in some sense, functions of parameters. Now, one step up, I guess that helps to the point that the expectation of that actually is equal also to phi, but that's only assuming that those are actually numerical things here. If you think of them as like true false, you shouldn't really think about averaging true and false in some sense. Okay, so moving on from that, the next distribution we'll talk about is the categorical distribution. So the categorical distribution is the sort of multivariate analog of the Bernoulli. It's categorical with k different, did I say k? Yeah, k different possibilities. So this random variable can take on the values between 1 and k. So here you have little x is some value in 1 and k. And I say that the probability that x equals k, sorry, I should say x equals I, not k. Probability that x equals I, parameterized by phi here, is equal to phi I. Okay, and here, the parameters that govern the distribution are actually a vector in Rk, right? Because actually, really, this should be more like a vector in 0, 1 to the k, because they all have to be between 0 and 1. And the sum of all of them has to be equal to 1. We also know that the sum for all I equals 1 to k of phi I equals 1. Okay, so this is also sort of very simple. We're just enumerating. I mean, it's sort of an obvious thing. All we're doing is we're just enumerating the different ways you can write, the different probabilities associated with each, possible assignment to that random variable, right? And this actually is, one of the more common distributions. Anytime you have categorical data and you want to model it probabilistically, it's probably the right distribution. It just says there's a different probability for each possible occurrence. A little note: we actually could leave out the last k, because we only have to sum to 1, so the last k could actually be implicit from the first k. We did that we already did that with the Bernoulli random variable, right? We just specified the probability equals 1, knowing that the probability equals 0 is just 1 minus that. We could do it here too, but it's a little less common. It's a little more common to just write them all, just for the sake of kind of ease of notation. And the last point, this is just also driving this home, is that it doesn't really make sense to talk about the expectation of a categorical random variable, right? Because you can't average together 1 and 3. They're not really, they're not numeric. They're just categorical. You can't average together sunny and rainy, right? So while I'm using sort of the integers to refer to the events, they're really just different categories of events. So you can't really talk about averaging them together. Okay, so now I'm going to go through several very quickly. I'm not really going to spend too much time on them because you can always look them up on Wikipedia or wherever else if you want to use them. But these are sort of the handful of distributions that I have seen. I've seen others too, but these are the ones I've seen most commonly used in data science tasks. So I'm not going to write them anymore. I'm just going to speak to them. And I'll say kind of what they're used for, and that's all. You can refer back to the notes on them if you want a little bit more detail. So the geometric distribution is a distribution of the positive integers, and what it actually is, it's actually the distribution of the number of Bernoulli trials it takes before you get to a positive one. So if I keep flipping a coin until I get heads, the distribution over the number of coin flips that I'll do is a geometric distribution, and the probability, it's again an infinite probability because over all possible integers. Right? It could take forever to get a 1, or countably infinite long time. But it has the same distribution of this phi parameter, and the probability is defined like that. And I won't prove it here, but it's pretty easy to check actually that this is actually distribution. It sums to 1 if you sum over all the infinite case. The Poisson distribution is popular for modeling the number of events that occur within a time window. So if I want to model the number of buses that arrive in a certain amount of time, the Poisson distribution is sort of a good one for that. This is the other sort of very common distribution over the integers that you may see in practice. It looks kind of like this, and this is the fun form for its probability distribution. That one's harder to show. Well, not that hard, but if you plug into Mathematica, it'll find it, for instance. But that also sums to 1 if you sum out that over infinity. The expected value, the thing you have to really know is it's parameterized by a single number, lambda. And it looks kind of like this. So it's kind of like a little bump shape like this. And its expectation is equal to lambda also. Okay, so now we're moving on from discrete, possibly infinite, but still discrete quantities to continuous valued quantities. So the most common distribution in data science, and I want to emphasize that this is not the most common distribution of actual data, it's just the most commonly one applied when people analyze data, for better or worse, is the Gaussian distribution. So I assume most people have seen this before. It's the classic sort of bell-shaped curve of probability distributions. It's a distribution that looks kind of like this. It's over the real, at least the univariate case, which we're talking about now. So over the real numbers. It has it's parameterized usually by two numbers, the mean mu and the variance sigma squared. So it's not at all obvious, and this is the density function. So you want to compute the density of a Gaussian. Given its mean and covariance squared at a certain point, you just plug in x into this expression, and that gives you the density. Now, this is not at all obvious, but it turns out that the expected value of this distribution, in other words, that would be for a continuous distribution, that would be equal to the integral from negative infinity to infinity of the variable itself times the probability, times the probability of x dx. For a Gaussian, this equals the mean. And if you compute the variance in the same way, that actually equals the variance there. So if I plug in my formulas for the expected value with this thing, and I put a mu out there, and I integrate that over the entire real line, I'll get 0. I'll get mu. And if I plug in, if I look at the expected value of the thing minus its mean squared, and I plug that all in and integrate it, I will get sigma squared. So we actually get, so it's sort of a natural parameterization because the variance and the mean are actually the parameters of the distribution, and they also are, in fact, the parameters they also are, in fact, the mean and the variance of the Gaussian. Now, that's not at all obvious, by the way, that's the case. I mean, why on earth, when you integrate this thing, do you get like a pi and an exponent and those things sort of canceling out to equal the variance? It's not at all obvious. The best way of doing it is actually with polar coordinates, but we're not going to cover that. It doesn't actually matter for any real sort of applications here, just as a fact that this is sort of how you get these terms. Now, what's nice about the Gaussian, actually sort of strangely looking at how complicated that looks, is that actually all these integrals work out very nicely. So there's some really beautiful properties of the Gaussian that sort of do make it a very nice distribution that people like to work with. Like you can oftentimes integrate it. It's a very nice multivariate analog, which we'll discuss next. But basically what it comes down to is that this thing is very easy to manipulate mathematically, and that's why people use it. It's not always the actual best fit to data. It just leads to some very nice properties that you can kind of verify. So be very careful when you think about using Gaussian distributions to actually make sure your data actually looks like this before you start applying the rules of a Gaussian distribution and assuming that kind of fits your data. There's an analog of Gaussians in higher dimensions. We'll actually see these later in the course when we talk about anomaly detection. We'll talk about mixtures of Gaussian models. But we're not going to worry about it just yet. I just want to throw it out there. There's an even more complicated expression that involves a multivariate now integral over all of n-dimensional space. But what it comes down to is the density of this thing, which is now a vector in n-dimensional space, can be defined similarly where this covariance is now a matrix, a covariance matrix of all possible pairs of covariances, and the mean is now a vector of all the different means. And this is a very sort of nice distribution, which we'll see a lot later in class, so I just wanted to mention it briefly now. The Laplace distribution is a distribution that looks like this. It looks a lot like the Gaussian. There's this exponential of negative something. But where the Gaussian has a squared term up here, so it's an exponential of a squared difference, the Laplacian is an exponential of an absolute difference. What this means is that the Laplace distribution falls off much more slowly. In other words, it has what are called heavier tails than the Gaussian distribution. It's not that heavy, the tails yet. They're still exponentially decreasing, but they're heavier than the Gaussian. So if you look at a Gaussian over the same range, you see that basically it becomes 0. And basically it falls off like negative, this thing squared, which is gets really small really fast. Whereas Laplacian distribution, hangs on for a little bit longer. So that's the difference there. And it's parameterized by some things like this, which is not quite the mean and the variance. The variance is actually the mu is the mean, but the variance is actually 2b squared. And it's also common. This is very common when you want to do things like when you want to represent a lot of things actually a lot of data actually looks more Laplacian than it looks Gaussian. For the exact reason that it tends to have heavier tails. So if you have a lot more outliers in your data, oftentimes Laplace distribution is better than the Gaussian distribution. Sorry, I called it Laplacian. It's just the Laplace distribution. I slipped into talking about Laplacians, which I often do. But this is just the Laplace distribution. Okay, and finally, the last one we'll talk about is the exponential distribution. And it's actually just the same as one side of the Laplace distribution. It's just the positive side. But it's just defined, it's always starts at 0 and only has sort of one side and also falls off like the exponent of just x. Not x squared, but just x. This one is, again, sort of useful for doing things like modeling. It's a common thing for doing things like modeling failure times. So, the time for something's going to fail, or the time I guess the time like a bus will arrive actually is oftentimes modeled as a exponential, or the time that like a part's going to fail. It tends to actually fit well in some cases to those kind of things. Again, not in all cases, but depending on sort of what you want to model, these things can be very appropriate. Now, what we'll see momentarily in class is that actually using these models will give you different machine learning. Using these models as a likelihood function, sort of as a model for your data, which we'll talk about in a second, actually give you different sort of machine learning models. So if you want to predict some quantity, it really is helpful to view what the distribution of that quantity is and use a distribution that actually matches that. So if it's Gaussian, you should actually use a Gaussian distribution to do your modeling. That leads to the least squares algorithm. But if it's different, you actually want to use a different likelihood, and then a different distribution. And that actually sort of ties together kind of probability and the notion of loss functions, which we've seen so far. But we'll see that in a second. Okay, so any questions so far? I'm going to jump now. Again, must be fast. These will all be kind of reiterated in the notes, but mainly it's just sort of to see them as a first pass. I'll go back to unfortunately, I should have done that before, because I'm going to go back to that thing a lot when I talk about maximum likelihood estimation. Okay, so let's stop there with distributions. Oh, I actually had one more slide. I didn't realize. So a couple others, which I won't even put up figures for, are the student t. It's like a normal distribution, but it has a little bit heavier tails. Kind of looks like a bell curve still, but has heavier tails. It's often used in hypothesis testing, which we'll cover next lecture. The chi-squared is a distribution. If you take a Gaussian variable and square it, that's a chi-squared distribution. Also very useful in hypothesis testing for reasons that we'll talk about a little bit next time. And I want to mention also this Cauchy distribution as well. So this is a very heavy tail distribution to the point where actually, if you compute this integral here, for a Cauchy random variable, this integral is actually not defined. It doesn't converge that integral. So it's sort of weird, but it has no expectation because it just has such heavy tails that its expectation but it's infinite in like both directions. So it's not even defined. So you can come up with, and actually some things are well modeled like that, but it's kind of fun, interesting to think that actually you can define variables that don't have an expectation, let alone a variance. Okay, so let's. So you probably don't want to use those in modeling anything. It's going to be kind of tough, but maybe your data really looks like that, and then you have to think about what to do. Okay, so let's switch gears then and talk about statistics from probability. So remember I said last time that statistics really were probability plus data. Okay, so when you want to fit data to a distribution, or fit a distribution to data, holding it the other way, you want to talk about somehow estimating parameters of a distribution. So we're going to go through this in some detail. Specifically in the case of the Bernoulli distribution, I'm going to derive the groundbreaking maximum likelihood estimate, which will shock you all, I'm sure. Then we'll talk about naive Bayes, which is an algorithm really based upon maximum likelihood estimation. And then finally, we'll talk about the connection between machine learning and maximum likelihood estimation, which is a really deep connection, actually. And it's also why it's a little bit odd not to talk about probability yet in this course, but we're finally going to join machine learning with probability, at least for a few slides, to give you some idea what's happening. Okay, so let's start off, though, with just sort of the basics of maximum likelihood estimation. All right, so here's the basic question that we have. Suppose I'm given some data. I have some data, x1 to xm. This is just now, there's no labels or inputs or outputs. It's just data points. And my question is, I want to find some distribution that models that data. Right? This is a common thing you might want to do. I mean, you probably are all thinking about doing things like this in your tutorial or in your final project. Of course, this is not a well-defined problem in general, right? In general, you have no idea what the distribution could be. It could just be that those points are the only possible ones. And it's just a discrete distribution with deltas at those points, and no other points are possible. And so you have some really weird, strange probability distribution, and you just happen to get those points. But in general, you sort of don't expect that. You expect there to be some sort of nice, in some sense, underlying distribution, and you want to find that distribution. So again, that's actually still a hard problem, even if you define nice to be smooth or whatever. It's very hard to do that. But what's not so hard to say is if we commit to a particular family of distributions, right, which I'll just write generally as P of x parameterized by theta. So theta are my parameters here. The question is at least a little bit easier. Funny enough, still not actually that easy, because there's still multiple ways you can estimate the same distribution from the same data. But it's at least a little bit easier. But the question now, so say that I have some data, and I want to commit to say, I think this is a Gaussian distribution. For the Gaussian distribution, the parameters are the mean and the variance. And so the question is, how do I find the parameters of that Gaussian distribution that best fit that data? And you might sort of already know how to do that, because the Gaussian kind of gives it away, right? It says, okay, it's the mean and the variance, and that happens to be right. But that's not actually an obvious answer at all. And what if you have a Poisson distribution? How do you find the best fit for that lambda parameter? It doesn't really have a good intuition necessarily, so how do you actually find that? So this is the core question of statistics in a lot of ways, right? How do I find parameters or a core question of statistics, how do I find the parameters that best fit a distribution? And there actually are many answers to this. This is not the only one. It's sort of an obvious one you can think of, but what we're going to talk about is not the only one, actually. So the principle that we're going to talk about here, and that is the most common and does tie together a lot of these different areas, and certainly, at least as far as data science is concerned, it's probably what you could, probably okay relying on this when you want to fit your distribution to data. But the idea here is that given the distribution P of x, so I have some data here, I have a distribution P over my random variable x. Remember, this is now a function that for any value will give me a probability. Then under this model, if I assume that all these data points are independent, and I assume they're all independent and distributed according to this same distribution here, and the probability of all my data is just equal to the product of probabilities under this model, right? Actually, I can write parameterized by theta here, which is equal to the probability, the product of probabilities, each one covered by that, of the different data points. Okay, so that's my probability of my data. I'm just using the fact that they're independent, which is a nice property that we had before. When things are independent, their distribution factors to the product of their different probabilities. Now, the idea of maximum likelihood estimation is really simple. What it says is we're going to pick the parameters theta that maximize the probability of the observed data. All right, so in other words, we're going to choose theta. We're going to solve an optimization problem, just like we did with machine learning, to minimize our loss. But here we're going to maximize over our parameters theta the probability of the data. In other words, the product from I equals 1 to m, the probability of xi parameterized by theta. And because multiplying probabilities is never a good idea, as you guys learned on the homework for natural language processing, if you did that one, it's more common to write this as maximizing the sum of the log probabilities. This is the equivalent, though, of course, to maximizing over theta, because the log is monotonic. So if you maximize the probability, you maximize the log of the probabilities too. Maximizing over theta, the sum. I'm just taking the log of this whole thing. So the product turns into a sum, and you push the log in the inside. The sum from I equals 1 to m of the log of p xi parameterized by theta. And this whole term here, we often write as L of theta. We actually, when we sort of want to emphasize the dependence on the parameter theta, we'll write it like this. And that term is called the log likelihood of the data. So the idea of maximum likelihood estimation is that we choose our parameters to maximize the log likelihood of the data. Again, this seems obvious, but there are actually other things you can do. There are other estimates, and I'll mention this briefly when we talk about Gaussian distributions, because if you've seen Gaussian distributions estimation, you've actually maybe have seen a different mechanism for estimating them that's not the maximum likelihood estimate. But before we do that, let me give an example for the Bernoulli distribution. And this is going to be, I will go in some detail here. We have 50 minutes left in class, so I'll spend some amount of time on this. Because I want to sort of emphasize how this works in some detail. So, this is fine. And the reality is when you actually are fitting these distributions to your data, there are packages in Python that you could actually just call that will sort of fit this thing. And we'll actually see those shortly in following class. But you'll just sort of take your data and you'll say, max, fit of this kind of model to your data. And that's fine. But I want to go through kind of where this comes from and how you would actually go about deriving this thing if you actually had to, figure out how to fit your data, fit distribution to your data. So I'm going to start with a really simple example, though, which is the Bernoulli distribution. So I have a coin, okay, and I'm going to flip this coin a bunch of times. I'll say I flip it 100 times, and it lands heads 40 of those times. So what would be the best estimate for the probability of this coin? If I flipped it 100 times and it comes out 40. It's not a trick question. It's a genuine question. What was that? 0.4. Yeah, seems like a good thing, right? You just take the number of total times it gets up heads. You divide by the total number of trials, and that's your estimate of the probability of that coin. That seems kind of obvious, right? So it's sort of the obvious answer. So a little bit more formally, right? If I have data x1 through xm, my estimate of my parameter, which I will often put a little hat over these estimates, would just be the number of ones I see over the total number, or in other words, the sum of all the xi's, because they're either 0 or 1, divided by m. Okay, so that seems like a reasonable estimate. But the question sort of is, why is this the case? What sort of principle are we basing that on? Because it's not actually that obvious, right? I mean, why? If we flip the coin once and it comes up heads, should we estimate it to be 100% heads? Right? I mean, there's some sense in which we might not think that. Right? I mean, we want to hedge our bets a little bit and maybe take, we want to say x10 plus 1 over m plus 2 to sort of have some bias that if we haven't seen anything before, we assume that it's going to be 1/2. Right? And this is sort of a philosophical question in some point, as in some sense. I mean, do you believe the coin to be unbiased? Do you think it's 50-50? Maybe if it is, you say, okay, 40 is close enough to 50. It's probably just random chance, right? So I'm going to say 50. It's only if it comes up, 80 heads or 5 heads, you really start to question whether it's a biased coin or not. I don't see many biased, despite the fact that we always talk about them in classes I have not seen many biased coins in my life. They're usually pretty fair. So maybe I would probably actually think this is probably 50-50 if I was flipping a real coin. But why might you? Why did everyone say, okay, we're gonna take 40 and say 0.4? And I would argue that everyone is sort of implicitly doing something like, or at least when you're asked the question in class, you implicitly do something like maximum likelihood estimation. So let me say why this is the case. Okay, and so it is. We're just going to go through this, and we're just going to do this. Okay, we're just going to kind of crank through this math, and I'm going to show you why it is a good idea, according to this principle of maximum likelihood, to actually estimate your Bernoulli parameter to be the number of heads over the total number of trials. Okay, so what we want to do with the Bernoulli is we're given our data set. We want to maximize over our single parameter phi. That's the probability of it being heads. The sum from I equals 1 to m of the log probability of xi, parameterized by phi. Okay, now here's a little bit of sort of notational thing again. What this really is saying is that this thing really is the probability that our variable x equals little xi, right? Because xi's are actual numbers. They're small xi's. That's the right thing to use. So how do we write that, this thing here? We can write it in a few ways, but one way to kind of write it is that this could be the sum from I equals 1 to m of the following thing. It is phi to the xi times 1 minus phi to the 1 minus xi. So this is a little trick to write it all consistently, because normally you have to say like the probability of xi being equal to 1 is phi. The probability of xi being equal to 0 is 1 minus phi. So to write that in a single equation, we play this little trick here, where we express it in both cases like this. So this is now a function of a little xi that captures both cases. So if little xi is 1, the probability of that event occurring, well, this term is going to be 0. So it's just this whole thing is going to be 1. This term will be 1, so this whole term will be equal to phi. So in other words, this whole thing here is equal to phi if xi equals 1, and 1 minus phi if xi equals 0, which is actually what we wanted. It's just a clever kind of way of writing it. It keeps us, lets us write it in one equation and not have to have like cases, because it's hard to differentiate stuff through cases. Okay, so let's go back to this now. I've left out a log here. Okay, so let's go back to this now. Let's now write what we actually want to optimize. So let's take the log. So now what we really want to do is we want to find the phi that maximizes the sum from I equals 1 to m of the log of this thing. And we just take the log now, so that would be equal to xi times the log phi plus 1 minus xi times the log of 1 minus phi. So again, our maximum likelihood estimate here says I want to find the phi that maximizes this whole thing, the sum of all those things. We actually know we could do a bunch of things here. Right? We could do things like gradient descent. We actually have done, we've already talked about how to maximize expressions. We could start with some estimate of this, take the derivative with respect to phi there, and take small steps in that direction. And we end up at a good place, hopefully, a good value for phi. That seems like a lot of work to have this amazing fact that you take the number of ones and divide by the total number. So this is one of those cases, again, like least squares, where there actually is an analytical solution that you can find by just taking the derivative and setting it equal to 0. So the way we're going to do this, so we want to maximize this. It turns out I won't show it, but there's only one optimum here. It's a single maximum to this thing. It's what's called a convex, or concave actually, because we're maximizing it. But it's sufficient to just take the derivative and set it equal to 0. So let's do that. Let's take the derivative of this thing. I'm taking the derivative of this whole thing. So the derivative of this whole thing with respect to phi of this thing Well, that's going to be the sum from I equals 1 to m of xi. Let's see, so xi, the derivative of the log is 1 over the thing in the log, so it's going to be phi plus 1 minus xi times the derivative of this thing, but there's also a negative sign touching that, so it's actually negative. So I'll just make this a negative sign minus 1 over phi. All right, now let's just distribute this out. So let's just say this is equal to the sum from I equals 1 to m of xi over phi minus the sum from I equals 1 to m of, am I missing it again here, of 1 minus xi over 1 minus phi. Okay, and now I know this is going to be optimized. So I set it to be equal to 0. So I'm going to set this. It's amazing how much work this is to show that you count the number of heads and you divide by the number of total things. But again, it's a good principle to know. All right, so I'm going to set this equal to 0, and I'm going to solve for this. I'm going to solve for what's the phi that makes this equal to 0. Let's just do that actually. Let's try to keep it all in this. Keep it all in the field of view here. Okay, so we want this to be equal to 0. We could write this actually. I don't know why I wrote this A's and B's here. That's kind of annoying actually. Let me write it down as without the A's and B's. Okay, so I can write this as the sum, 1 over phi times the sum from I equals 1 to m of xi equals the sum equals 1 over 1 minus phi times the sum from I equals 1 to m of 1 minus xi. Right? That's the next step I would do there. That, of course, is equivalent to saying that 1 minus phi times sum over I equals 1 to m xi equals phi times the sum from I equals 1 to m of 1 minus xi. Right? And now we just sort of group terms that depend on phi here. So we'll just sort of expand this here. So we have actually I guess I see why I did that, but it's not that much. So okay, so this is the same as saying that the sum from I equals 1 to m of xi minus phi times the sum from I equals 1 to m of xi equals phi times m, right? Because you have that there. So phi times m minus phi times the sum over I equals 1 to m of xi. Sorry, am I missing something here? No, I think that's right. Okay. So this now now let me look at all the terms that depend on phi here. So the terms that depend on phi will be equal to, something's weird here. What did I mess up? No, that's fine. Okay, let me just do it like I have in the slide so I don't confuse myself. But this way, let me just for the sake of argument here, call this thing, how did I do it? I called this thing A. Okay, so I called this A, and I called this B. Right? And now what I have is I have the expression, I think I get sums all kind of annoy me here. I have 1 minus A, so 1 minus phi times A is equal to phi times B. What was that? Not visible again. Okay. So I'm calling this whole thing here A, and I'm calling this whole thing here B. I have this expression here. I'm just rewriting it in a way that I won't screw it up. This is the same. Of course, now I'm just sort of grouping terms together. The solution here, I mean, now it's pretty straightforward, right? Now it's just sort of saying A minus phi A equals phi B. In other words, phi is equal to A over A plus B. Okay? So now we go back to what our A's and B's were. So our A was the sum. See that? Okay. So our A was the sum of over all the xi's, and our B was the sum over of the 1 minus xi's. So this term here, so this is equal to the sum from I equals 1 to m of xi over the sum from I equals 1 to m of xi plus the sum from I equals 1 to m of 1 minus xi. All right, and this is, of course, this term in the bottom here is just m, because every term we're either adding 1 or 1 or adding x or 1 minus x. So this whole thing equals the sum of I equals 1 to m of xi over m. Okay. So I finally, even after confusing myself, this is, again, the point that this is sort of almost absurd how much effort this takes, to show the amazing fact that if you want to find the maximum likely estimate of a Bernoulli random variable, you just compute the number of ones you see divided by the total number of things you see, period. Right? So that's all I've been showing there. But it is important to sort of drive that point home, because this is a general technique for doing these things. So what this is saying is that if I have sort of any distribution, or actually what this says here for Bernoulli's in particular, is that if I have a Bernoulli distribution, the reason why you all sort of thought that, you should take the empirical sort of average as your Bernoulli parameter, the empirical sort of average of the zeros and ones, is because that's the quantity that if you look at the probability of the data being generated by a Bernoulli model, that parameter estimate actually maximizes the probability of what you've observed. Okay, so actually let me pause for a question now, because I think this sort of drives home some of these points. And the question is, suppose that we observe some binary data, and we compute the MLE in the Bernoulli under the Bernoulli model. I'm also going to say that there's at least 1 0 and 1 1 there. And I'm asking which of these following are true. So the first says that if I pick any other parameter, I have the fact that the probability of the data, of every data point under this other parameter is going to be less than the probability under the true one. I have the fact that the product of probabilities under any other thing is going to be less than or equal. Actually, this really should be supposed to be strictly less than. I think that was a mistake. There should be strictly less than in both cases. Let me edit that right down the slide. But with strictly less than, let's change that. And 3 is saying there's always one case that essentially violates this. So these two are exclusive, or you can only choose one of this or one of this one. But then this one, you can choose yes or no for that one as well. This one says that there's at least one point where the probability under some other one is bigger than the probability of that one. These are all, again, necessarily true. I think they're supposed to all hold with strict equality. So let me change those. Put it back up. I won't change the Piazza poll. I copied I copied LaTeX from the Piazza poll, so it'll say the same thing, but you can change it in your head. So let me go ahead and open the Piazza poll. Let me actually, hang on, let me actually stop this. I'm going to clone the poll because a lot of people have voted already. Let me close it. I'm gonna clone this. And we'll go from there. All right, so looks, yeah, this one is high. It's like the highest I've ever got in the class so far, I think. 94%, I like it. And that's good too, because that one is literally the definition of maximum likelihood estimates. So it's good people didn't get that one. Did indeed get that one right. All right, so does anyone want to argue for or against this one? Number 1. Who thinks it's, well, does someone want to argue for it, why they think it's true? Someone want to argue against it, why I think it's false? This one was pretty clear cut, actually. Someone has to have an opinion. I'll sort of start calling on people. Maybe that's going to... Yes?
So it's like a coin flip, right? So because the two P's are not equal to each other,
Uh-huh.
means that in the first case, the number of heads we got is not equal to the number of heads we got in the second case. So we have the probability of X equal to
But I'm not actually talking about the probability of... this thing is actually... The data is all the same. Right? The data is the same through two things. This is just the data, the probability of an observed data point evaluated under two different probabilistic models. Right? So maybe there.
since both 0 and 1 are here, and the phi's are different, that means like either one the probability of 0 for one is less than 0 for the other, or like one time greater, or one.
Okay. Yeah, so maybe can decide if I want to add any to that, because I think that's pretty good. That's right. And that actually answers both the first and the third one also. So the third one is true. There's always one. And that actually, maybe it's probably easier to show the third one than it is to show the first one. But the third one, of course, implies the first one is not true. So what's happening here is that what we're really modeling is we're modeling the probability, and it doesn't even matter what the data is. All we know is there's 1, 0 and 1, 1 in there. Because the probability that x equals 0, given phi, that's just phi, right? And the probability that x equals 0, given phi, sorry, x equals 1, given phi prime, is just phi prime. Right? We know that there's 1, 0 there. So if these are not equal, so we know there's 1, 1 there. So these are not equal. And if phi prime is bigger than phi, then for the 1, this has higher probability. So it's important to understand what's happening here. So for any given single example, the probability of that example is just governed by the parameter, right? Phi or phi prime. That's the probability of that single data point. So if there's a 1 and if phi prime is greater than phi, then of course this one has higher probability than that one. On the other hand, if phi is less than phi prime, phi prime is less than phi, then the opposite happens, right? Because the probability is 0 of phi equals 1 minus phi, and the probability that x equals 0 given phi prime is 1 minus phi prime. And so the other one will have higher probability. So it's really important. This is actually a really important point. This is why I had this on the quiz. The probability of any given data point is, of course, maximized by, in this case, by just picking phi equals 1 or phi equals 0. Right? But that would actually make the whole data have 0 probability, because you would have some term that would, its probability is 0 then. And so that would be a very bad estimate for the whole thing. So you can always make the probability of any given point really high by just fitting that point's distribution, essentially making the probability always hit that single point. But that is not the goal of maximal likelihood estimation. What maximal likelihood estimation does is exactly this middle one. It's maximizing the sum, the sum of the log probabilities, or equivalently, the product of the probabilities. And that's really the key point of what maximal likelihood estimation is doing. Okay, so that's was the point of that whole exercise there. Okay, so I don't think there's time for this. I won't do it now. But all I'll say is if you do the same exercise with the Gaussian density function, and you take derivatives with respect to mu or to sigma, set them equal to 0, what you will find, and this is really actually not obvious except maybe in hindsight, is that the mean, the best maximal likelihood estimate of the mean, ends up being the mean of the data points. And the maximal likelihood estimate of the variance ends up being the average of the variances. Now, if you've seen other estimates, you may have seen a case where there's an m minus 1 term down there. That's actually a different kind of estimate. That's what's called an unbiased estimate. And that has a different rationale behind it. And there's a different reason for using it in some sense. But we're not going to use that here because the maximum likelihood estimate is just this. So that's just, I mean, if you've seen that before, just know that that's just sort of driving this point home that this is not the only way of estimating these things. It's just one sort of natural way. Okay, so now with the rest of the time we have left, I want to talk about machine learning kind of in the context of probabilistic models. And I'm going to start off with talking about naive Bayes. So naive Bayes, I'm using it here because it's a machine learning algorithm that's really rooted in probability. What we're going to do is, by the way, we can interpret it as a hypothesis function, a loss function optimization. We'll talk about that in a second, actually, in the next section about how you define machine learning algorithms in terms of probabilistic models. But I'm going to take a little step back here and define it in terms of sort of a pure probabilistic setting. So the basic idea is that we're going to take our inputs here and think of them as random variables. And for the sake of this lecture, I'll just consider them being all binary, both the output and the variables here will be binary random variables. Or actually, no, I think I'm going to make them categorical. Let me verify, which I actually did. No, I made them all binary here. Okay. So, of course, these could be categorical. These could be binary. These could be Gaussian, too. But our goal of this whole thing is to estimate the probability of y given x. Okay, that's sort of similar to our machine learning ideas, except instead of trying to minimize like a loss of hypothesis function, now we're trying to explicitly predict the probability of the different outcomes given x. Now the way we're going to do this is we're going to do this with Bayes' rule. So we're going to use the fact that the probability of y given x equals the probability of x given y times the probability of y over the sum over all little y's, the probability of x given little y, and the probability of y. So we're just using Bayes' rule. We're not going to model that first explicitly. We're going to instead model the other terms within Bayes' rule there, and use Bayes' rule to compute our probabilities in the end. And this is sort of the just so far actually we've made no real assumptions. We're just talking about kind of general predictions of probability. With the naive Bayes, now this is still sort of a complex thing, right? Because if we try to model this whole thing, kind of the joint distribution over all possible features, that's even with binary cases, right? That's we're modeling, the probability of there's n different features here, so we're modeling 2 to the n different combinations. So that could be actually very sort of intense to try to model the distribution here of all x's even given a value for y, even if all these things are binary, right? So what the naive Bayes algorithm does is it makes an independence assumption. It assumes that the features are conditionally independent of each other given the class. In other words, it assumes that this equals the product from I equals 1 to n, p xi given yi. Okay, and that's, when we have that assumption, this is called the naive Bayes algorithm. So let's see how this actually works kind of in practice. This is actually all you need to know the naive Bayes algorithm. These 2 equations are really all you actually need to know. What we're going to do is we're going to explicitly model each. So we're going to model p of xi given y for all I. And we're going to model p of y. We're going to use those 2 probabilities to sort of model our data. Now let's again consider the case where y is binary here. And we'll suppose x is also binary. They're all Bernoulli. The way we do this, of course, is now with some Bernoulli distributions. So we're going to model P of y with some, I call it phi 0, I think. And we're going to model P of xi given y equals 0 with some Bernoulli parameter phi I, right, like this, phi I 0, and then the probability of x I given y equals 1 with phi 1 I. Okay, so all I need is this is going to be one distribution. These are going to be 2 n distributions. So I just need to keep track of 2n plus 1 different Bernoulli distributions in order to compute sort of all the probabilities that I have here. Yeah, question?
Why don't you do the distribution of
Yeah, so the again, and this is sort of comes back to the assumption. Oh, you mean px by itself? That's a good question, actually. Yeah, so why don't we need px by itself? We actually don't need that because we can compute that from these terms. Right? So remember that px here is equal to marginalizing out over y. So if we want px, we don't need it for the final thing because we can just compute those terms. But if we want it, we can just sum over all values of y. Y is just binary, so we can do that sum. And we can compute p of x that way. Now, it's actually important. Well, there's one sort of important point. P of x. So let's actually, this is a good point. In naive Bayes. So again, the naive Bayes assumption is that the xi's are conditionally independent given y. This does not imply that p of x is conditionally independent. He says this is not implied by it because, as we talked about last time, conditional independence does not imply marginal independence and vice versa. So p of x is actually a very complicated distribution, and it's best represented in terms of summing out over the y's here. Okay. So how do we do this then? Well, at this point now, we just have this many Bernoulli distributions. We can just compute them with the exact thing we already saw, maximum likely estimation. So I'm not going to go through it. It's the exact same math as before. I won't put you through that again, or myself through that again. But for example, if I want to estimate the Bernoulli parameter for the y values, I just look at the sum of the y's divided by the total number of things. If I want it for one of the x's, well, now I actually have to condition on the fact that we're either talking about the case that y is equal to 0 here. So what ends up happening there, and this can be easily shown again through maximum likelihood estimation, but it's also pretty intuitive as it was in the previous case, that what you do is you actually, if I want to estimate y equals, for y equals 0, I only look at the cases where y equals 0, and I just sum over those ones. I just take the average over those ones. So if I want to compute the probability that xi equals 1 given y equals 0, I just compute the average of the xi's in the cases that y equals 0. All right, so actually, maybe I'll just say this, do this slide first. So let's go through a few of these actually by example. This isn't a poll, but we'll just ask them. So I have this data here. What is p of y equals 1? We'll only do a few of them because they're all the same. But what's p? What's this first one? What's p of y equals 1, which is just equal to phi 0. What is that? This line is one we're actually going to predict, so ignore that. This is a testing point, or a validation point, maybe. So it's just the other bits of the data. 4 by 7, right. What is p of x1 equals 1 given y equals 0? This, by the way, is the parameter phi 0, 1. Phi y equals 0. What is it? 1/3. Right? We just look at the ones where y equals 0. So that's this one, and that one. And there's one time where this is equal to 1. And so, again, the maximum likelihood estimate, the value of that parameter, which maximizes the likelihood of the data under this model, ends up being just 1/3. Okay, so we won't go through the rest of them, but the rest all sort of work in the same way. When it comes to prediction time now, though, so now I'm given a new data point. I don't know what the actual output is. How do I predict what it is? Well, the way I do that is I just apply Bayes' rule, right? I know that the probability that y equals y, given x equals little x, is equal to the probability that y equals y times the probability that of x given y, which is the product of the probabilities of xi, xi equals little xi given y equals y, product over all those things, divided by this thing on the bottom, this term here. But the point I want to make here is actually this term here is the same. I'm going to do this. I'm going to compute this term here for each possible value that y could take on. Right? I'm going to compute it for y equals 0, y equals 1. If y was multivariate, was categorical, I would do it for 1, 2, 3 up to k. But the denominator, the thing that sort of this divides, is just this is really p of this is p of x I equals x. P of x equals x. We can't factor that one. But importantly, it doesn't actually depend on. This is weird. This is now crooked a little bit here. Interesting. Doesn't actually depend on y at all. So what I can actually do is I can just compute the top terms, and that's just, by the way, this product here of parameters, right? Because all those probabilities are just defined by those parameters there. I just compute those, and then I know that the sum of all those things for all the y's has to add to 1. So I just compute them and I just sum them up. I compute them and I divide by their sum. And that gives me the probabilities if I want them. In fact, computing them all together and dividing by their sum is exactly what the denominator actually is. So you might want to just look at that a little bit, but basically what it means is that you can just look at sort of just add up all those terms on the numerator, and then kind of just normalize them, and you have a distribution over your possible outputs. Also, if you just want to make one prediction, you can just find the biggest of those. You don't even have to normalize them. You just pick the biggest one of them. One more quick note about naive Bayes, or two quick notes. As before, don't compute products of probability, so don't actually compute this thing. These terms are all going to be quite small. And if you compute them, you'll probably have numerical overflow if you have any reasonable number of features. So instead, compute their logs too. And then, either you can normalize it in log space, actually, that's also possible to do. Or you can just pick the maximum one of the logs if you want to do that. Number two is the same thing that happened with n-gram models, if you remember. That if you've never seen a word before, you have 0 probability, which will, if you take the log of 0, it blows up. So you might want to use something like Laplace smoothing again to basically add a little bit to the numerator and the denominator here in both cases. And that might, on new data points, like the ones you haven't seen before, you've never seen an xi equals to 1 in this particular coordinate before, you should do this to avoid the case of things blowing up in that setting. Okay, so now the last thing I'm going to say is that about naive Bayes, before I think I'm going to have to be kind of brief on the next section, unfortunately, is that the reason, so naive Bayes is often just sort of framed as counting, right? And it's sort of given from first principles. It's just, well, obviously what you do is you just count the probabilities, and you basically just fill out tables like this, right? We go through it, and these are all probabilities, and then you apply Bayes' rule, and you kind of get the answer. The reason why I go through this sort of effort of deriving maximum likelihood values here for all these things is that it turns out it's just as easy for there to be any other distribution for the x's themselves. So they could be, I mean, we saw Bernoulli, right? But they could also be categorical. That one's easy. They could also be, Gaussian. They could be Laplace. They could be, Poisson distributed. It doesn't actually matter. Because in all cases, what you can do is you just basically compute maximum likelihood. Your formula is still the same. You're finding a maximum likelihood estimate of the parameters of the distributions to maximize the likelihood of the data under this model. And so if they're Gaussian, you have basically mean estimates of the Gaussian for just that one variable in y, and you have variance estimates of the Gaussian for that one type of y. And that is how you do naive Bayes for Gaussian data points. So if your data points are real valued, you do something like that, right? This is a very powerful kind of paradigm, thinking about this in terms of maximum likelihood instead of just thinking about it in terms of counting. Because naive Bayes really is quite powerful beyond just counting. And understanding that it is actually, what it is actually doing is just prescribing this model here, where these distributions are whatever you want them to be, and the y has to be categorical. You can't have continuous y's. That one's, then you would need an infinite number of these things. But as long as y is discrete, you just have a separate one for each value of y, and things kind of work out nicely. So that's the fundamental idea of naive Bayes, and it's often actually a surprisingly good algorithm. And we'll talk later, and I think we're going to have to, unfortunately, finish even this up next time a little bit. But we'll talk a little bit about how it's connected to other machine learning algorithms. Okay, so in the 5 minutes I have left, I want to just, and actually maybe this is enough time, 6 minutes or so. I want to emphasize the connection between machine learning, as we presented it, and maximum likelihood estimation. Right? So the first case is this weird model we talked about called logistic regression. So why on earth? So I said logistic regression was, remember now we're going back to our parameters of machine learning, minimizing losses of hypothesis functions. And I said, okay, logistic regression is you minimize this logistic loss where it's this thing. That's our loss function there. Okay, so where did I come up with that, and why was that chosen as a loss function? So where it comes from is actually a probabilistic model. So what logistic regression hypothesizes is that y is binary valued. So here we're modeling p of y given x, where y here is binary valued, and the probability that y takes on the value +1 given x, so given x equals x, and parameterized by the parameters theta of our model, that is just equal to 1 over 1 plus the exponential of theta transpose x, negative theta transpose x. And it's actually for y equals -1, there's no negative sign there. So we can write this all as, for y equals little y, this equals this times y. Okay, that's sort of a nice way, a compact way of writing that. So what logistic regression does is it sort of hypothesizes this model of this. Okay, so this is our probabilistic model. And now, given this model, we want to perform maximum likelihood estimation. Given this model and some data, we want to perform maximum likelihood estimation to find the parameters that make the observations most likely under this model. I should also add, this is called a sigmoid function here. And I meant sigmoid, not logistic there. This is a sigmoid function. It sort of is this sort of S-shaped function that goes at 0.5 at 0, goes to 0 this way, and goes to 1 that way. So if I want to maximize over theta the probability of my observed data, yi's given xi, and theta, this is equivalent to to maximizing over theta the sum. Oops, there's a product here. The sum of the log probability of yi given xi theta, which is also equivalent well, okay, if I take the log of this thing, this is log of 1, so it disappears. And then I have the log of this thing on the bottom. It would be negative that thing. So if I want to maximize the negative, it's the same as minimizing just the thing itself. So this is equivalent to minimizing over theta, the sum from I equals 1 to m of the log of 1 plus the exponential of negative yi times theta transpose xi. Okay, so this is the connection between this probabilistic model and this loss function. And this is, of course, exactly this logistic loss. Okay, so now you could also, of course, say, like, okay, well, why did we pick this weird loss, this weird probability there? You know, that's sort of passing the buck, right? And actually, there is a reason for that too, but which I won't cover here. But actually, there's some justification for that model in particular, and sort of this nice thing that sort of models probability as well between being 0 and 1. And so there's some other nice reasons as well. Basically, this is where we derive the logistic regression model from. It also means that when we're done fitting that model, we have more than just a hypothesis function. We actually have a function where we can plug into this equation here and give a probability estimate of how likely we think the positive class is versus the negative class. This is actually why people like logistic regression so much, is it actually gives you a probability, unlike, say, support vector machines, which aren't really interpretable in a probabilistic manner. So this is the sort of the connection, again, between these probabilistic methods and machine learning, which we already covered. Least squares, and I might just be able to finish this so we can move on to something else next time. Least squares are actually the same thing. The least squares model says that I'm going to hypothesize that my data, I have x and y's, and I'll just leave it here, and I won't write it down just to say it. But I'm going to hypothesize that my probability of y given x is equal to, well, rather my y really is equal to x transpose theta plus some normal random variable with mean 0. In other words, y is normal with mean x transpose theta and variance sigma squared. And if you plug that in to the Gaussian likelihood, you take the log of that, look at the log likelihood. What you get when you maximize the log likelihood is you're actually minimizing the sum of squares. We won't really, that's actually really easy to see. All the terms drop out except the exponential term. Then there's an exponential of a square. You take the log of that, and so all that's left is those square terms that depend on, this is the ones that depend on theta. And importantly, what this is saying is that least squares regression is the maximum likelihood estimate assuming your data is Gaussian distributed. Now, what this also means is that if your data is not Gaussian distributed, least squares is often a very bad thing to do, because it means that you're minimizing some you're maximizing some likelihood that's actually it's not a good fit to your data. And so other approaches, like, say, absolute loss functions, come out of distributions like the Laplace distribution. So by changing the type of model you use, you effectively get a different loss function for machine learning. And that really is the connection. This is probably the most common loss function, actually, in machine learning. It is the log probability of the data under some model. And this is the connection there. Okay, so next time we're going to talk about hypothesis testing, and we'll kind of move on from probability and statistics, at least a little bit.